Section 18 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 13, Part 1. The Earth. The conception of the Earth formulated by the ancients assumed it to be a flat disk floating on water, which idea persisted in some form or other despite various phenomena clearly impossible of explanation upon such a hypothesis. After some more or less vague speculation on the shape of the Earth by Thales, circa 640 to circa 546 B.C., a clear and rational idea was advanced by Pythagoras, who flourished in the 6th century B.C. and taught that the Earth, in common with the heavenly bodies, was a sphere, and that it received no support at the center of the universe. The idea of the sphericity of the Earth was doubtless derived by analogy from the appearance of the Moon. The theory became an established part of Greek science and philosophy, and consequently has continued to the present day, anticipating by some 2,000 years the acceptance of the belief in the Earth's rotation. In fact, the spherical form of the Earth figured prominently in Greek astronomy, and the division of the Earth into zones and the idea of poles was promulgated by the Alexandrian philosophers, and even before their time. Indeed, not only did they realize the shape of the Earth, but also its size. Eratosthenes, 276 to 195 or 196 B.C., whom we have already mentioned in our chapter on pre-telescopic work, made one of the first scientific measurements of the Earth, obtaining a result which must be considered the first good geodetic measurement. He found, from the application of simple geometry, that the angular distance of the Earth's surface between Alexandria and Cyrene must be 1/50th of the circumference of the Earth. Posidonius, who was born about the end of the life of Hipparchus, made a new measurement of the circumference of the Earth, much after the fashion of Eratosthenes, but reached a value too small. One of the crucial arguments for the sphericity of the Earth is that when a ship sails away, the hull first disappears from view, while the masts are visible. This was first advanced by Pliny, 23 to 79 A.D. From the Greeks and Romans to the Arabs may be a far journey, but little was done in the study of the Earth until the Arab astronomers of Baghdad, under the patronage of Caliph al-Mamun, made a series of measurements of a meridian of the Earth, which agreed with those of Ptolemy. These measurements virtually sufficed until Willebrord Snell, 1591 to 1626, a Dutch mathematician who had discovered the law of the refraction of light, made a series of measurements of the Earth's surface, from which he computed the length of a degree of a meridian to be about 67 miles, an estimate subsequently corrected to about 69 miles by one of his pupils, and differing but a few hundred feet from the value now accepted. A measurement by Richard Norwood, circa 1590 to 1675, of the distance from London to York, made in 1636, enabled a degree of latitude to be obtained with an error of less than half a mile, and finally Picard, in 1671, made a measurement of this quantity, which we have seen was sufficiently accurate to be used by Newton in computing the mass and motion of the Earth and in demonstrating his law of gravitation. This outline shows that the spherical shape of the Earth was constantly held in mind by scientists for about 2,500 years. Other views of the Earth's shape also obtained. The idea of a flat Earth had to be vigorously opposed by arguments founded on experiment, observation, and discovery. After the phenomenon of a disappearing ship, one of the most important of the arguments against the flatness of the Earth's surface was based on the different elevations of the pole star in the sky, depending upon the position of the observer. Now, the pole star and the surrounding stars, though they may be at different heights in the sky, form the same pattern wherever on the Earth's surface they are seen, thus showing that they are immensely distant, and that lines from all points of the Earth's surface directed to the pole star would be parallel or have the same direction. As one travels north, it is seen that the pole star sinks lower and lower in the heavens, or has a greater angular distance from our zenith. If the Earth were flat, this would not be the case, for an angular distance of 7½ degrees difference in the position of two stations 520 miles apart in a north and south line would mean that the star is only 3,450 miles distant, which is manifestly impossible. Furthermore, it is a well-known experience that in crossing the Atlantic from England to the United States, the Sun by a watch rises an hour later for every 600 miles we travel west. If the Earth were flat, the Sun would rise at the same instant over its entire surface. To answer both these conditions, namely the sinking in the heavens of the pole star and the equal delays in the time of sunrise in traveling equal distances, a round globe is required. Still, the globular form of the Earth was not accepted generally until after the historic voyage of Christopher Columbus and that epoch of exploration and discovery which resulted in the circumnavigation of the Earth in 1519. After the demonstration of the sphericity of the Earth came the determination of its exact figure by the systematic measuring of arcs of meridians. When the results were mathematically examined, the conclusion was reached that the Earth was not a perfect sphere, but flattened at the ends, or in other words, that it was an oblate spheroid. Newton, in his Principia, published in 1687, showed from theoretical considerations that the Earth bulged out at the equatorial regions. On the other hand, in the following century, in 1745, the Cassinis, who were leading astronomers of France and deeply interested in the measurement of the Earth's surface, maintained that the Earth was contracted at the equator and bulged at the poles, or in other words was prolate. The difference in the two ideas being concisely expressed by Professor Moulton, who likens Newton's idea of the Earth's figure to an orange and that of the Cassinis to a lemon. It is interesting that Newton's proof of the oblateness of the Earth anticipated the direct observations of the astronomer and geodesist. Today it can be demonstrated in simple form by means of observations of the time of vibration of a pendulum, such as are carried on systematically by such scientific agencies as the United States Coast and Geodetic Survey. It is possible to supply various mathematical proofs of the oblateness of the Earth in connection with its motions and with its relations to the Moon and to the solar system. But these hardly concern us in the present pages, and we may dismiss the matter with the assertion that the ellipticity of the Earth, as determined by Harkness in 1891, amounts to 1/300th as compared with a value of 1/295th established in 1866 by Colonel Clark of the English Ordnance Survey and accepted for many years as a standard, and 1/230th as was given by Newton for the ellipticity of a meridian section of this oblate spheroid. Clark's spheroid of 1866, which is generally adopted in geodetic and other computations, would give a radius at the equator of 3,963.307 miles and 3,949.871 miles at the poles, these figures having been slightly corrected in 1878 in the second place of decimals. The radius of the Earth is in many ways a fundamental measure, especially in astronomy, and for that reason its determination is a matter of no small importance. Thus, observations made with a view of finding the distance of the Moon, when discussed and reduced, simply give us this distance in terms of the equatorial radius of the Earth, so that to determine the distance in miles we must know the number of miles in the Earth's radius. As a consequence of the spheroidal shape of the Earth, a degree of latitude as well as of longitude varies with the point at which it is measured. Thus, at the equator 1 degree of latitude is equal to 68.704 miles, but at the pole a similar degree is equal to 69.407 miles. The difference in a degree measured on the parallels of latitude, which are small circles, is of course obvious, and while at the equator a degree of longitude amounts to 69.652 miles, at latitude 40 degrees, or approximately that of New York, 40 degrees 43 minutes, it would equal 53.431 miles, and at the North Pole it would decrease, of course, to 0. Newton, in his researches on gravitation, by comparing the attraction exerted by the Earth with that of the Sun and other bodies, was able to connect its mass with that of the planets and Sun. The problem of determining the mass of the whole Earth in terms of a given terrestrial body, that is, in tons, pounds, or kilograms, was indeed a serious one, and it was first attacked in Great Britain by Neville Maskelyne, 1732 to 1811, who was Astronomer Royal. If we know the volume of the Earth and its density, referred to some standard as water, air, or iron, it is of course easy to determine its mass. But the determination of its density is no less a problem than the determination of its mass directly. It is possible, of course, to compute the relative amount of water, but this gives only a small amount of the mere surface of the Earth. We can descend in mine shafts a mile or more and investigate the nature of the material, but this again affords no clue to the thousands of feet of materials below, so that an estimate of the average density based on such data cannot be considered at all trustworthy. Newton, taking into consideration the various elements of the Earth, estimated its density at between 5 and 6 times that of water. Maskelyne, however, bearing in mind the phenomenon of the deflection of the plumb line observed by Bouguer and Le Condamine in their expedition to measure an arc of latitude in Peru, a phenomenon caused by the attraction of the mountain Chimborazo, selected the narrow ridge of Schehallien in Perthshire, and found that the attraction of the mountain caused a deflection of about 12 seconds on each side of the ridge. This attraction of the mountain, as compared with the attraction of the Earth on the plumb bob, enabled a value for the density of the Earth of about 4½ times that of water to be obtained. It remained for the famous Cavendish experiment, carried out by Henry Cavendish, 1731 to 1810, to substitute for the mountain a pair of heavy balls. This gave a value for the density of the Earth of 5½ times that of water, a value confirmed by numerous repetitions of Cavendish's classical experiment. Expressed in pounds, the mass of the Earth is a little more than 13 billion, a figure that the human mind utterly fails to grasp. There must have been a time when the Earth contained much more heat than at present. The Sun is not supplying heat enough to make good the losses sustained by the globe. These losses must have been taking place over a period of countless years. One is forced to believe that not only once was our Earth much hotter than at present, but that its temperature was a red heat. Going back still further, the now solid globe must have been actually a molten mass. Being a molten mass, it is not difficult to realize that it readily assumed a globular form on its journey through space. A falling drop of rain is a globe. A drop of oil suspended in a liquid with which it does not mix has a spherical shape. Therefore, if a mass of material as large as the Earth were so soft that its individual particles obeyed the forces of attraction exerted by each part of the mass on all the other parts, it is quite obvious that it would assume a globular shape, especially under the influence of motion. If this great sphere were caused to rotate around its axis like a ball of clay on a potter's wheel, any lack of true sphericity would not only be overcome, but there would be a tendency for the molten body to bulge at the equator and flatten down at the poles, forming an oblate spheroid, such as by actual measurement the Earth is found to be. Indeed, not only is the Earth an oblate spheroid, but most of the planets which can be measured have become flattened at the poles for the same reason. In connection with the spherical shape of the Earth, mention should be made of a recent theory which seeks to demonstrate that the shape of the Earth is being transformed into a polyhedral form, or more exactly, that there is a tendency in the direction of its assuming the figure of a regular tetrahedron or four-sided figure, each of whose faces is triangular. This is manifested by the lithosphere or solid portion of the Earth. The water is massed on the faces of such a tetrahedron, the force of gravity acting most powerfully at the center of each of the four surfaces. The tetrahedron hypothesis assumes that a more or less solid crust was formed when the Earth was still perhaps in an approximately spheroidal form. As contraction occurred in the interior, the external shell proved too large. Hence, a different form has to be assumed, which it is asserted would be the tetrahedral. On each of the faces of such a tetrahedron one of the four oceans would lie, the Arctic Ocean being assumed as the fourth for the region about the North Pole. The continents would correspond with North and South America, Euro-Africa, Asia-Australia, and Antarctica. This hypothesis is borne out in many respects by geological and other considerations. First advanced in the 70s of the 19th century by Lothian Green, the hypothesis has been put forward in recent years with further developments and attempts at its proof, so that it is considered as a tenable and possible explanation, though its absolute soundness has not been demonstrated. Recognizing and proving the spherical shape of the Earth by no means explains the apparent motion of the sun, moon, and stars as regards the planet. As the nature of the solar system was developed by Copernicus and Newton, people were compelled to recognize that the Earth revolved around the sun, and furthermore that it rotated daily about its axis. These motions are necessary to explain various phenomena. For example, when a body moves in a circle, a force is needed to act on it, pulling toward the center proportionally to the square of the rate of spin, and proportionally to the distance. Every pound of mass in the moon would need a pull equal to about the weight of 3 ounces to keep it in a circle which it traveled around once in 24 hours. Every pound in the sun would need a pull about 3/4 of a hundredweight. The nearest fixed star would need a pull on every pound of about 9,000 tons. One cannot imagine that the Earth could exert such forces, and so are obliged to think that the Earth is revolving and not the sky. Final proof of the rotation of the Earth was furnished in the middle of the last century by Foucault. His experiments were constantly repeated in physical laboratories and experimental lectures. From the dome of the Pantheon in Paris he suspended a heavy ball by a fine cord and caused it to swing in a single plane. The path of the ball across the floor could be traced, and it was found that after it had been in vibration for some time it was swinging in a different direction from that in which it had started. The reason was that the floor had revolved under the ball with the rotation of the Earth. The daily rotation of the Earth on its axis and its yearly rotation about the sun supply us with our means of measuring time. According to Professor Poynting, quote, "The Earth is a clock. The line to the sun is the finger, and the sky is the face. But the Earth is not a regular timekeeper. Our 24-hour day is only the average between successive noons, or times when the sun is due south. If compared with a good clock, the sun is in parts of the year too soon, and in other parts too late, sometimes as much as 1/4 of an hour. This cannot be due to change in the Earth's rate of spin, for to change a spin there must be either a force acting at one side of the center of gravity or a change of shape. The forces on the Earth exerted by the sun and moon act almost exactly through the center of gravity, and so affect the rate of spin hardly at all. The Earth does not change its shape sufficiently to account for the variation in the solar day. The variation in the solar day is due partly to the inclination of the Earth's axis to the plane in which it moves around the sun, partly to variation of the Earth's motion around the sun at different times of the year. The fixed stars keep good time, getting round in about 4 minutes less than 24 hours. By them clocks are rated. Their day is the true time of one rotation of the Earth." Unquote. End of section 18.